And welcome to today's webinar. I'm Melissa Romero, Forensic Science Consultant and CNE and Media Group. I will be moderating today's event, a technical framework for materials by design in enterprise R&D. This educational webinar is sponsored by Enthought. Enthought has been at the forefront of scientific computing for 25 years, helping define modern computational science. They specialize in scientific AI ML solutions for enterprise R&D and are known for their unique expertise in the complexities of scientific research, R&D data, and software engineering. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a balanced, accurate, and timely fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the help widget at the top right corner of the screen or type your query into the Q&A box. If you're disconnected during the webcast at any time, please log in again according to the instructions that you had received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. This webcast also allows certification of participation. To receive your certificate, please click on the certificate icon below your Q&A box to download your copy after watching the webinar. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars, and each webinar will be archived at CNEN online after the live webcast. During the presentation, we will be hearing from Dr. Michael Connell and Dr. Michael Heiber. Dr. Michael Connell is Chief Operating Officer at Enthought and holds an MS in Electrical Engineering and Computer Science from MIT, plus a doctorate in education from Harvard University. He is a learning scientist with a background in robotics, artificial intelligence, software engineering, and education. He is passionate about using data science to solve practical problems, from data mining to predictive modeling to adaptive learning design. Michael is a former software design engineer from Microsoft and has also served as a faculty member at Harvard University, Dartmouth College, and the University of Texas at Austin. Dr. Michael Heiber is Director of Professional Services and Customer Success Materials Informatics at Enthought. Dr. Michael Heiber holds a PhD in Polymer Science from the University of Akron and a BS in Materials Science and Engineering from the University of Illinois at Urbana-Champaign, with expertise in polymers for optoelectronics applications. He leads Enthought's Materials Informatics technical team and supports customers in large-scale MI initiatives. Prior to joining Enthought, he worked as a postdoctoral researcher at several institutions where he developed improved physical models for organic electronic devices that connect complex materials microstructure to semiconductor device physics. And let's get started. I will now turn it over to Dr. Michael Connell.
Thanks, Melissa. So I'll be doing the main presentation, everyone, and my colleague Mike will be joining me in the Q&A. First, I wanted to thank you for joining us today. We are Enthought, and we've been in business for 25 years. We started out building what has become basically the infrastructure for modern scientific computing. So if your team is using Python for machine learning or data science or that kind of thing, then they've almost certainly used some of the open source libraries that we helped to pioneer, like NumPy and SciPy, excuse me. And while we have deep roots in software like that, our main focus really has been on applying those kinds of technologies to build scientific AI solutions. And we work mainly with R&D organizations in materials, advanced materials and chemistry, as well as in the life sciences to solve hard problems that really accelerate the R&D process and then help those organizations to get different kinds of competitive advantage. I did want to highlight that one of our big differentiators is that 80% of our staff have STEM PhDs, and that means that we aren't just IT people. We're scientists who code, and that means that you don't have to waste time kind of translating chemistry when talking to us. We can have high bandwidth conversations about your science and translate that directly into solutions. All right, so I thought I'd start by defining what materials by design is and doing that in contrast to traditional R&D. So traditionally, R&D has been a trial and error process, really, where you guess a recipe, you synthesize a sample of that, and then you check whether the guess was right. and you tweak the recipe based on the results, and then you go around the horn again until you find something that works. And then you hope it keeps working as you scale up. So you can think of, in this sense, you can think of an R&D organization really as a kind of a specialized, human-centric, expertise-dependent search engine. I'm talking about your whole R&D organization as a kind of a search engine, where you're searching through a space of formulations to find materials that have the properties that you're looking for. And the components of that search engine are really spread out across your whole organization. So there are different, data systems at different places. There are various measurement devices with their dedicated PCs. There are lots of different people. So there's a chemist who synthesizes things. There's going to be someone who does the analysis and evaluates the sample, and that may or may not be the same person. There's going to be someone in manufacturing who determines the manufacturability. There are financial people who are assessing economic feasibility. And so it's really akin to, you can think of it as an analogy, think about a group of hikers, right, that are looking for valuable minerals on a mountain. And each of them has kind of a different piece of the information or the knowledge, the expertise to determine if any given rock is one of those minerals. And you're searching on the mountain at night without a map in the fog. And that's kind of analogous to, you have this machine that's capable of doing the search, right, for these formulations. But really, the components are spread across your people, your workflows, your tools, your data systems. And so by contrast, materials by design is really taking these same components. You already have the pieces to do this work, taking them, but transforming them so that instead of guessing inputs and checking outputs, you invert that process so that you specify the outputs that you want. Usually it's performance properties of the material and things like that. And then the system guides you to a recipe that will produce those properties. So from a human standpoint, that process has been inverted, right? They're doing design, looking at the outputs and being guided to the formulations necessary. So returning to the hiking analogy, in the extreme, in the limit, right, this transformation goes from hikers in the fog on an unfamiliar mountain to a single robot that's traversing a mapped terrain in full daylight. Where you tell the system what you want, and it'll guide you to a good, or even in some cases, an optimal recipe. So this obviously is faster, but you can also do a lot better, right? So not only are you using your information more effectively, that you know about kind of the space that you're working in, but when you have these kinds of dramatic efficiency gains, you get to choose how to use them, right? You can capture them as savings. That's usually, though, not the big win. The big win is in being able to search more of the terrain so that you can get better quality results. You can increase your innovation. But you get to make those choices about how to leverage the capabilities. So this is kind of a conceptual framework for thinking about what is required to make this transformation. There are really three fundamental requirements, no matter how you approach this. First, you have to specify the space that you're working in, the design space, right? It's kind of like defining what's the geography that we're kind of searching in. It has inputs. Those are things that you can control, the ingredients, polymer ratios, could be process parameters like temperature and pressure. And then there are outputs. And ideally, the output shouldn't just be an objective property. This isn't a prediction model or problem. So it's not a property like viscosity, but it would be a specification of a quality metric on the property that you care about. So what does good viscosity look like, right? That's the metric that we're talking about. So getting the inputs is fairly straightforward, right? Because you know what you have control over. Defining what good looks like can actually be somewhat challenging in some cases. Sometimes it's straightforward, but sometimes it's quite hard. The second thing that you need to do, so that's specifying the design space. If you just specify it, then it's going to be full of invalid solutions, right? There are going to be formulations that aren't synthesizable, not manufacturable, not safe enough, not cost effective enough, et cetera. And so you have to shape the space. And what that means is you incorporate all of the information that you have about the problem and its solutions into the specification of the design space. Things about safety, economic viability, manufacturability, synthesizability. Those things are often the way we kind of handle the complexity of R&D as a search process, is we decompose it and people have different roles. And so I do my part and I say, yeah, it's got the right properties. And then I hand it off to someone else to do the next part. The more that you can actually build that in to the problem specification itself, the better it's going to be, the more effective it's going to be, the more efficient it's going to be. And that information is in your system already anyway. You're applying it. So shaping the space in this way has a couple of benefits, important benefits. One is that it shrinks the search space. So you're blocking off areas that aren't going to be viable. For example, what's manufacturable. If you look at the data, sometimes you can do an analysis to draw a boundary and say, below this line's not manufacturable. The person synthesizing it shouldn't pass on anything that is in that region. So you can kind of do that kind of thing to shrink the space, but it also ensures, you can think of it as kind of a density of valid solutions in this space. Ideally, you want to get to the place you've added all the information. Every point in this design space is a valid solution to your problem. It won't all be optimal, but they should all be they would all be viable if you have enough information to do that. And that's great, because if you have a limited design budget, you can kind of essentially take any point out of the space. And if you have a bigger design budget, you can search for more and more better solutions. So anyway, you're aligning the space with kind of the problem requirements. The third step is then you obviously have to navigate this space to either search for a solution or in some cases to find an optimal solution. So this is typically expensive in two ways or three ways. One is it takes a lot of data to build a representation of the full space. The second thing is it's expensive to run some kind of a search process over it sometimes. The third way is if you don't do the alignment in the second step sufficiently or at all, you may have to run that expensive process many, many times to find a solution that's valid or to validate that it's one of the better solutions. And so these three steps all kind of hang together as an approach. There are, however, methods that you can use to reduce the cost and complexity of this dramatically. So as one example, I already kind of described how if you add information to the space, you're reducing the size of the search space and you're increasing the density of valid solutions. So that means fewer iterations in your search process. Another example is there are actually techniques you can use on the third step, where instead of trying to learn the whole space before you start your search, you only learn the part of the space that you're searching. So the search and the learning are happening simultaneously. Okay, so again, this is a general conceptual framework for thinking about this transformation from kind of this human-centric search process to more of a machine-driven design process. All right, so bringing it back to the definition, I already said that traditional R&D is a human-centric, trial and error, iterative search process. Materials by design is this transformation of that system that makes it more target-driven, more of a target-driven design process. And so I just kind of went through conceptually the steps that are involved in executing that kind of a transformation. It's important to note, though, that it's kind of a big undertaking in most cases, right? It's not going to happen overnight. Not only, and there are things that go beyond just rolling out technology. Obviously, this is a big change management effort. You have to bring people along. You have to redesign workflows and stuff. So the good news is that you can actually get substantial value in the short term by focusing on the key foundational components that you need to put in place in order to build the new machine. And if you work on these components and build out all the pieces, you can do that in version, which is kind of the big payoff, but you can also get a lot of value along the way. That's important because you have to keep yourself and all of your other stakeholders happy, right? Like, what are you doing over there? We don't want to wait 3 years to show value. You need to show regular value along the way. And so the point is you can do incremental things that are valuable. If you do them right, they're moving you towards something. If you don't do them right, you're getting incremental value, but there may not be a way to kind of pull all the pieces together in the end. All right, so the three areas that form the foundation for doing this are your data, your predictive models, and your analytic workflows. That means preparing and managing your data, implementing or improving predictive models for that step where you go from formulation to sample, or sample evaluation, let's say, and then automating your analytic workflows. And the overarching theme here is kind of shown on the right, is that we have to make each of these components more machine operable, right? Which involves a process. As I said, you've got all the pieces in your current distributed human-centric search process that is your R&D organization. You have to find those pieces. You have to make what's implicit in people's heads explicit. You have to codify it in software, Those are two different steps and require special, skills. And then you need to make them operable by a non-expert human. That's a good step. If a non-expert can operate the system, then you're very close to, if not already at the point of being able to have the machine be able to operate it. And then within here, it's kind of a hierarchy of sub-problems, right? You've got this top level thing you're trying to invert, but inside of it, there are all these sub-problems, right? Your data, your predictive models. And inside of there are embedded some other inverse problems. Those tend to be the thorniest problems. They're the most expertise dependent. They require the most iteration. And they really are bottlenecks to trying to kind of invert the overall problem. So as a couple of examples of that, NMR and XRD analysis are inverse problems that are embedded in this whole hierarchy. So you have an unknown input, which is the molecular structure. You have known outputs, which is the diffractogram or the spectrum that they produce through the measurement process. And what you're trying to do is figure out what were the inputs that generated these outputs. So again, those are among the most thorny problems in the middle of this. They're the most expertise dependent. They're the biggest bottlenecks. So again, it's valuable to solve those in their own right, but automating them is critical to kind of being able to do the larger transformation that you're looking to do. Okay, so how do you do this? There's no universal sequence for how to do it. It depends on where you are. It depends on your domain. It depends on your digital maturity, what you've tried in the past. It depends on the emerging technologies and what capabilities they kind of afford us. So LLMs, for example, may change, the way that people kind of go about this. What I'm going to walk you through is a typical sequence of events that we've followed with many of the customers that we've gone down this path with. So the starting point, as I said, is this intuitive search, right? It's manual trial and error. It's based on human intuition. That's our baseline for comparison. And so the first step beyond that is what you might call data augmented search. And by search here, I mean R&D is a human-centric search process, right? It's that searching for the formulation for your product. So the first step is usually to get your data in order. Compiling your historical data, it's scattered across Excel spreadsheets. It's on the measurement machine, the PCs attached to your measurement devices. It's in people's heads. It's in notebooks. And you need to also, to complement that, you need to create access patterns that are friendly to scientists. One of the biggest sort of problems that you have in terms of friction is scientists getting access to data. When they have an idea, they need data to try and validate it or explore it. If they have to go through SQL queries, either you have a small number of scientists who can do that, or you've got another interface. You've got some person in the middle who's got, a database administrator certificate, who's got to be the person who's the go-between, and that creates massive friction on this whole process. So they should be able to query the data directly, but they should also be able to do it ideally in the domain language. Talk in terms of polymers, talk in terms of functional groups and stuff, instead of in terms of like SQL tables. So we've been doing that for decades, literally, and creating APIs that are sort of domain oriented and creating the tooling for scientists to do that. It's getting significantly easier today, with LLMs being essentially a kind of a universal semantic layer that you can wrap around these systems. So it just gets better and better as we get new capabilities. All right, so once you have the data, you can start to there are kind of a series of things that you can do to get more and more value out of it. And so one thing to think about is, how do I find a starting point, right, for any formulation problem? Well, one common thing that we do is what you can think of as kind of a nearest neighbor keyword search. So compile the data, give tooling to the scientists to say, what are all the projects we've done in the past that are most similar to the project that I'm trying to do now? And then let's look at the formulation that was the solution to that problem, and we'll use that as our starting point. Maybe it'll solve your current problem, or at least it's a good starting point. So that's kind of nearest neighbor keyword search. You can go beyond that, and you can start to use modeling around the data itself to interpolate, right? You can find a better starting point than any you've seen in the past. So that goes beyond just kind of looking at past experiments. Then so keyword search isn't really based on the meaning. It's based on superficial features that describe the problem. It uses polymer A, but you might actually care about the content of it, or the meaning meaning can take different forms, but meaning-based search is more of a semantic search. Things that are close to each other in keyword space, like think of a card catalog in a library, right? Just because two things are alphabetically near each other on the shelf doesn't mean they have the same content, right? And so it's really about the meaning that you're looking for. It could be about the function of the molecule instead of the some kind of the polymer backbone or something. So anyway, you can do this meaning-based search. We've done that very successfully. In one example, there was a process that people were using, kind of keyword search. It took weeks and sometimes failed, and they had to escalate it to senior people. They were senior people who should have been working on the next gen product, were spending about 40% of their time actually handling this troubleshooting on the line. And we were able to kind of give them a better set of tools where they could search by meaning. They could find the result in seconds at a much higher hit rate. And so everybody was happier. Customers were happier. These guys could focus more on the next gen work, et cetera. So that's another step you can take, semantic-based search or meaning-based search. And then there are other things that you can do that make the search more intelligent as well. So not just kind of forms of search, but how do you also use that information in other ways? I already kind of alluded to this idea that we collected the historical data, and one of the things we found was that they hadn't been tracking manufacturability because the chemists were just synthesizing against their requirements for the functional properties. And it turned out that a lot of them were not manufacturable. They'd give it to the next group and they would have to they'd have to test it in an application. And they couldn't, the viscosity was wrong for it. So we took the data, we did an analysis, and we found that boundary where things were or were not manufacturable, and you can build that into the system. And so they stopped doing that. And that increases the throughput, it decreases the number of iterations you have to do. So that's an example of also using the data to make the search more intelligent. So the big theme here is really stop reinventing the wheel, maximize the value of the data that you're collecting by treating it as a first-class strategic asset instead of like, this is just a side effect of our operations that people may go back to for some reason, but treat it as a first-class object that's actually collected, curated, and made accessible for primary and secondary analysis. It's also important that you're capturing your institutional knowledge when you do this. So that makes it not only available to other scientists and preserves it for business continuity as people come and go, but it also lays the foundation for machine-centric operations in the same way that it does for people. All right, the second step is what we might call prediction augmented search. So in your current R&D process, there's one or more steps where you have to go from a candidate formula to evaluating its properties. And historically, right before digital, that meant an expensive physical trial. Usually it's expensive. They can be very expensive or they can be kind of expensive. Mixing chemicals at a bench, making a sample, and then measuring the property like viscosity or tensile strength or whatever you care about. Okay, so we can accelerate this by replacing as many physical trials as possible with virtual replacements. And this kind of augmentation can be achieved in multiple ways, right? All of them are predictive models. The first thing is, are there off-the-shelf simulators? Are they good? Are you using them effectively? So there are still, these things exist, obviously. Often people don't trust them. There's a calibration problem, like, sure, I use the simulator, but I have no idea if it's actually a good simulation of my problem. And so you can do things with existing simulators, like calibrate them. So there are steps you can take there. Sometimes they're insufficient. They're not high fidelity enough. You can't calibrate them. We've seen cases, and I'll show you one of our case examples, where the chemists working in industry know more physics than is in the textbooks, which means it's more physics than is in the simulator, certainly for the domains and regimes they're working in, but they couldn't extend it. So there are reasons, good reasons, to sometimes build your own purpose-built simulation. And then the third thing is, once you have a good simulator, typically, you can generate large volumes of data that you could use to train up synthetic data to train up a machine-learned surrogate model. And the reason to do that is that it's 10,000 times faster than a physics-based model or bench experiments. And so the reason this step is important, or valuable, I guess, in the short term, is you can start to screen large spaces virtually. You can fail faster and cheaper, but again, you're making it possible for the machine to operate the whole machinery of R&D at this step without human intervention, or with less human intervention. All right, the third step you can take is automated data analysis pipelines. And so this obviously is a source of classic expertise bottlenecks. You've got one person who knows how to evaluate the data. You've got one person who knows how to look at the image and say, yes, that's a good one, or no, it's not. And so what you want to do, ideally, is automate the entire sort of data to insight lifecycle, from the point where you collect the data through analysis, evaluation, and then determining what's the next step as we go around to the next iteration. And importantly, and you can kind of see a dependency between steps here that kind of guides how this stuff gets laid out in time on the roadmap. A secondary benefit is that having this infrastructure also allows you to continuously feed data to the predictive models. So there are two important things there. One is they're data hungry, right? They get more accurate the more data that you can feed them, but the world keeps changing. And so you need to also keep them calibrated. Machine learned models aren't like rule-based models of the past. They're, so for example, when your supplier changes, lot number, or you change suppliers, the impurity profile of your inputs, your ingredients may change, and so your models will drift against reality, and so you have to keep them calibrated. So you can see that there's kind of connections between these different stages. Anyway, the theme here is to accelerate cycles, remove bottlenecks, free up scientists' time so that they can focus on higher level problems. And so these three steps are, data, predictive models, data analysis pipelines. They have the immediate benefit of accelerating that human-centric iterative search process that most labs are running today. But it also does lay the foundation for making this transition to more of a compute-centric inverse design process, where many of the details of the forward process are kind of encapsulated by the machine so that human experts can back up a level and they can really focus on the material design process. And so on this side of the line, post kind of inversion or post-transformation, there are really two stages that we can think about. One is what we can think of as machine-directed discovery, where the system generates candidates, but there are still some steps that are facilitated by humans. Typically, the last steps are to validate, empirical validation of candidate formulations to make sure that they, in fact, do meet all the criteria. But there's also steps like data collection, empirical data collection by the system to calibrate it. Now, there may be other steps along the way, right? So it doesn't have to be 100% in order to start seeing this as a machine-directed process. But this is really a continuum, right? Until you get to the ultimate end here. Oh, sorry. So, and the theme here is really to, once you've encapsulated, so part of the reason the system works the way it does is because there's so much complexity in doing the R&D. We try and control the complexity by chopping it up into stages, right? Linearly decomposing this very complex problem into stages. And that means that people are kind of focused on one piece at a time. That's actually by design, right? Because that's how we're getting humans to be able to solve a part of the problem so that the whole problem can be solved. If you can solve a much larger piece of the problem, humans can back up and start handling these complex trade-offs. That's what I mean by stepping back and thinking of it as a design problem, is dealing with sort of the complex trade-offs among variables and stuff, instead of kind of trying to handle one variable at a time in a linear process. So the logical endpoint of this is the self-driving lab. There's not really anywhere else to go with R&D and technology once you have the self-driving lab, which is running 24/7, it's closed loop, it's doing autonomous discovery. The AI plans, executes, learns from experiments 24/7. It's like, tell it what you want, wake me when you're done. So that's kind of a continuous discovery of even non-intuitive materials, because it's so much more efficient and using the information so much more effectively that it can search more broadly and expand kind of the innovation envelope there. So that's, like I said, that's kind of the logical endpoint of this whole thing. All right, so a few case examples, and I'm gonna march through the three on the left and then one to the right of the transformation line there. So this first example of data augmented search is a formulation problem. It happens to be in the life sciences, but it might as well have been in materials. In this case, the company is testing medicinal compounds. And in testing, they have to be administered intravenously, which means that the scientist has to come up with a solvent that will dissolve the compound without interfering with its functional properties, right? Whatever the therapeutic effects are, and it can't introduce toxicity. And so the lab had, and this is a common problem, every time you're doing a new compound, you have to test it at some point. And so the lab had no organized database of prior project data. And so they did have some scattered data, notebooks, ad hoc Excel files, people's heads, but mostly what was recorded were the success cases. They didn't have any failure data on this. And so what would happen is junior scientists would come in, and it's so expertise dependent and so kind of specific to their area of work, is that they would struggle, they would fail repeatedly, and often they had to escalate it to a senior person, or they would have to outsource it. So this creates delays, it creates bottlenecks, it creates extra expense, but that's how they kind of got to know how to do this at a more expert level, was to struggle with it. So the solution that we built was to compile the historical data, that's the first thing, and set up their data collection so that the new data was also going into the system. Since they didn't have a lot to bootstrap from, we also extracted expert rules from the experts' heads and started capturing all the complete data so that this thing could refine itself over time. And so in the end, it could recommend valid starting points for these solvent formulations, solving the starting point problem and allowing these junior staff to operate at more of an expert level. And then it continued improving over time as more data were collected. So you can see there are kind of elements of other parts of it, of the kind of process, but the core thing to look at here is compiling the data, making it accessible to people, right? You're elevating the level of the junior people to that of senior people. You're making use of the data. All right, so the second thing is this predictive augmented search. In this case, we're working with a customer in the semiconductor industry. They make photoresist. So the way photoresist works is it's what they use to print the circuit on the chips onto wafers. So there's a substrate, a wafer substrate, and they kind of coat it with their material, which is the photoresist. And that material interacts with light. And so they want to print a pattern, which is like the wires of the chips on the wafer. And so they shine a light through a mask, which has the pattern that they want on it. And where the light interacts with the photoresist, it changes its properties, and where it's in shadow, it doesn't. That's actually how you lay down those very thin wires. And so in fact, the properties they care about for their material are things like how wide of a line does it lay down, right? Because this is not an extrusion of metal process, right? The way you would do for telephone lines or something. This is a chemical diffusion process. And so it's got some randomness, and you're not sure what the line width is going to be. You can't control that directly. The other thing is that you get some variability in the line width roughness. So these are the critical dimensions. These are the features that they care about for their material. There are off-the-shelf simulators. There were a few problems with those. One is that it's expensive, and they had to buy per seat. So there would kind of be one designated person, or you have to have some scheme. You can only run one thing at a time. So you're paying license costs on top of the compute costs. The second thing is they knew physics. It didn't cover the physics that they knew. It wasn't high fidelity enough for what they wanted to do. They knew stuff from doing the work. They wanted to add it, but they couldn't. There was no mechanism to extend what the simulator was able to do. The third thing is that they actually needed it not only in 1D, which is what the simulator could do, but they needed it in 2D because they have square patterns and they have round patterns, holes that they also need to measure. And they care about cross sections because this diffusion process varies over the depth as well as, across the surface. And so they couldn't handle these 2D and 3D geometries. So the solution here was to develop a custom predictive model, a simulator that they could also extend with their own. Well, first of all, it handled the 1D, 2D, and 3D geometries, but they could extend it with their own proprietary physics. And because they own the code, we wrote the code on top of open source libraries, with custom algorithms for their use case. They owned all that code. They could run it on the cloud without any per seat licensing costs. So of course, now it's higher fidelity. That means they're going to use it more often. It's less expensive. That means they're going to use it routinely. But it also means you can start opening up new capabilities. Like you can start actually doing multi-objective optimization. You can start doing some inverse design by doing things like mapping the efficient frontier between two different properties that trade off against one another. And so all of these things are valuable in the short term, immediately in their kind of current process, but they also are again, making it possible to start moving the machine forward toward materials by design in sense that now the machine can do a lot more in the virtual space without having to check with the human doing the empirical experiments, since they haven't fully automated that part of it. And the second thing is you can start generating a ton of data, and you can start thinking about things like building surrogate models off of this. So the important point is that, yep, you get efficiencies in your current process, but it's also creating new affordances. It's opening up new capabilities. All right, so the third category here is automated data analysis pipelines. This is again from the semiconductor industry. This is photoresist. And so historically, the way that the analysis piece was done is you would make your material, your photoresist, you would print a test pattern onto a wafer, and then you would scan it with a scanning electron microscope. That's what's shown over here, to create an image of it that a human could look at. And then these humans, these PhD chemists, would go to the machine, and they would use digital calipers to measure the line width and to measure the line width roughness. There's a lot of variability there. Even one person measuring the same thing twice would have some variability. They could only do a small section of a large pattern because it was so time consuming. And when we did a later analysis, we found that the statistics of that small swatch they were doing were not the statistics of the whole pattern. So they weren't getting representative statistics. There were all kinds of issues with this, in addition to the just the cost of doing it. So it was a major bottleneck. So what we did is we automated this whole pipeline. You submit your wafer or a series of wafers, and then you go back to your desk and you get to analyze the data, because what happens in the middle is the machine is now connected to the data system, the data management system. The first thing it does is it gets alerted that there's a new measurement coming off the machine, a deep learning neural network that we trained to figure out what data analytic pipeline should we run. Is this holes, is it lines, is it squares? And so that would trigger a particular set of algorithms to measure the features that matter. And so you can see here some of the code, and then that's overlaid. The actual kind of measurements that the image processing algorithms were doing are shown here. And then it would extract the measures that mattered, and it would put them directly into the database. So the researcher could just go to their desk after lunch and they could come back and pull the data. We also made this extensible as well. The physics are changing that they're working in as the science changes, the kind of requirements change. They can do more. They need new test patterns. Customers are demanding more capabilities. Maybe they need to extend it with new features. So we set this up so they could extend the detection piece, and then also extend the kind of analytic workflows that followed that. And it's not they don't have to learn to be software developers. They just need to learn enough scientific computing, basically, to express what they're doing, right? They're part of the problem into code to do that analysis. So this is an example of automating the data analytic pipeline there. And again, it takes it from hours of work to seconds of work. It also captures that institutional knowledge in code, which reduces the risk of that knowledge walking out the door as people retire or move around or whatever. So there are those immediate benefits, but obviously there's a lot more that the machine can now operate as we're thinking ahead to kind of that inversion. All right, so I had 4 bullets in terms of like making things ready to be more compute centric. So you can do this, you can invert the problem. The 4th one was you have these embedded inverse problems in the middle of it. I already mentioned NMR as an example of that. So this is a case example of that. NMR analysis is critical for kind of understanding the composition of complex materials. This case was solid state electrolytes for batteries, I think, but it's difficult to perform. And so our solution enabled not just an expert to do it, which is how it used to be, but any scientist could perform at an expert level to do the NMR analysis. And so the application incorporated a combination of physics and machine learning to match the best experts' manual NMR analyses. And so it could perform the analysis automatically most of the time. So you get reliable and insightful metrics in seconds. You eliminate the frequent multi-day delays that were caused by scheduling conflicts, or either the machine or the human, freeing up expert time and then reducing mistakes that cause expensive rework, because you get much more reliable kind of readings from this. Okay, so that's an example. So that's an example of inverting one of these thorny problems in the middle of that. All right, so those are the 3 that kind of accelerate the human-centric process. So let's look at an example where we're pulling those pieces together into more of a unified system that's starting to look more machine-directed. So at the center here, we have the data system, right? So it's got all the historical data. It's got all the new data feeding into it. And we'll talk about that in just a sec. But the first thing is it uses the historical data to find a better starting point. And then it uses predictive models to run through, right, and find a candidate, a better candidate. And so it does as much of that work as it can. And it produces a recommendation for a recipe and a prediction about what the properties of that recipe will yield. So those two things go through the loop. You could automate this, so this could be an automated system. It wasn't at the time that we wrote up this case. So a human would do the experiment, and they would collect the empirical data. And now you have a pair. You have the synthetic data, the predictions, and you have the empirical results. Those get stored in the system together. You use the empirical data to go back and refine the model, right? Increased accuracy and continue to keep it calibrated with a changing reality. So that's the product development loop. And you can see it's much more machine directed now. You have a secondary loop here, which is the system then is monitoring how are the predictions of this system. And if they're good, just go on about your day. But if you find one that is different from the prediction too much, right, too different, then you can raise an alert, and either a group of humans or agents or combination thereof would discuss and analyze, like, why is there such a big miss? What's missing from the model? What's off about the model? So it might be something like, well, we didn't account for the ambient temperature in the room because we didn't think of it as part of the experimental conditions, but it is, or whatever, right? Like, you come up with new descriptors that you can add to the model, you update the model. So here you have a product loop that's machine directed, and here you have a process improvement loop on the back end. And so this is the kind of thing that you can do after you've built some of the individual components to bring it all together. All right, so to wrap up, I'll just kind of walk through some of the big takeaways. If you only take a few things away, let me try to highlight what they could be. So the first thing is that there's a mindset shift that needs to happen here, right? We have to stop thinking about relying on human-centric guess and check kinds of workflows, and which again are kind of manual human-centric search engines, and move toward these high-performance compute-centric design processes where humans are acting as designers at a higher level. They're faster, they're cheaper, they're better, they're more innovative. And so the components are valuable, but inverting the process is where the big multiplier takes effect. So invert the R&D process is where the big win is. We want to stop searching in the fog, and we want to start designing in the light. The second thing is, the theme is really to capture institutional knowledge, right? It's a key step in moving from human-centric to compute-centric, but it also recognizes that your organization's greatest asset is your expertise, right? Which is often embedded in your data, but it's really the decisions behind what data points to collect and that sort of a thing. It's often trapped in people's heads, and by shifting that expertise into code and into the models, you can do three things. You remove those bottlenecks, you mitigate the risk of business discontinuity as people come and go, and you build a system that accumulates intelligence. It gets smarter with every experiment, and importantly, it's also critical to making the system more machine operable, because when I showed you the picture of the parts of this machine are spread out over the whole system, that's kind of some of the biggest pieces of the machine are those pieces that are in people's heads. All right, so the third point is it's kind of a reassurance that, or it's almost a note about the hedged risk here. You're doing this. You have the pieces of the machine to do this. You're doing it as a kind of manual open loop search process. This is a process of finding those pieces, codifying them so that you can reassemble them into something else. You don't have to invent all this new stuff from scratch. And so the goal really is to connect them computationally in this way so that you can kind of make this transformation. And so what you're doing is you're making better use of the assets you already have, right? And you're getting that multiplier because you've taken them to the next level. The fourth point here is really start small for quick wins. People aren't going to sit around saying in 3 years we're going to have this big ta-da. It's a journey. It's not a cliff. And you don't need a massive big bang transformation to see the results, right? So I showed you through the case studies that delivering these individual components, data augmented search, custom simulators, automated analysis, those can yield immediate ROI that's quite substantial. It can do it today. But it can also move you if you do it in the right way with this kind of mindset or this frame in mind. It can move your organization toward more of a, well, toward that ultimate vision, right, to getting to kind of inverted design process. And then finally, this is not really in the presentation, but it's just a note for those of you who are involved in or tasked with coming up with the AI strategy for R&D. I would argue that in R&D and materials R&D in particular, it's generally better to define your strategy this way, like we're moving toward this endpoint of materials by design, instead of saying this is our AI strategy, and then you can figure out how AI can help you get there, how AI can help you get there faster and better. Having the right framework at that top level can actually make developing the strategy, whichever strategy it is, a lot easier. This is one of the things we hear is we've got to come up with an AI strategy. And it's like, yes, that's true. But that gets a little weird because it's kind of like we've got a hammer and now we need a strategy for what we're going to do with it, as opposed to this is our business, this is our strategy. How does AI plug in as the current wave of tools? Because we've gone through lots of waves, right? We've been doing this for 25 years. When cloud computing comes in, when the web comes in, when all of these things come in, the basic problem doesn't change. It's still the same sort of endpoint that everyone's moving toward, but what you can do with it does. And so AI is another set of tools in that toolkit, I would argue. So anyway, to the extent that that's useful for those of you who are involved with that, I wanted to offer that as a final note. All right, I think we can shift now to the Q&A.
Thank you so much, Dr. Michael Connell. What an excellent presentation and very informative. And now we're going to ask Dr. Michael Heiber to join us. Here he is. Hello, Michael. I was telling them earlier, this is my first moderator duties that I've had where I've had both presenters with the same first name. So we're going to go through this Q&A and we'll try to do Michael C or Michael H or what have you. But thank you both for being here. And now I just want to remind the audience that you can ask questions through the Q&A box on your screen. And with that, we will now open it up to our first question. This audience member states, search by meaning makes sense, and asks, can you elaborate what it takes to build a system like that on the practical aspects?
Mike, do you want to take that one or you want me to?
You can start.
Yeah, so there are different, like I said, there are different kind of forms of meaning. So I'll give you two examples. So in one example, people were searching by keywords and they were kind of looking for prior project. Okay, so they had machines they deploy into the field, machine fails, what went wrong, right? And so there are kind of categories of failures, and they had a database of all the sort of tickets that they had collected in the past for troubleshooting these kinds of customer problems on the line. They were searching by keywords saying, you know, it burned the wafer or it scratched something or whatever. That's a keyword search. It's kind of superficial features of, you know, the symptoms. What's better is if you can actually search for, I need things that look like this, right? You can actually draw with your finger or something, you know, an image, and you can say, what are all the projects in the past or all the tickets in the past that somewhere in them contain an image that looks like that. So that's more of a content-based search, which is, I would consider a kind of a subcategory of meaning-based search. The one that's kind of more popular to talk about right now is, you know, embeddings in machine learning models and neural networks are a form of meaning-based search, where instead of searching again by superficial features that you describe through text or something, you actually are, you're creating a separate model of the space, the search space, which preserves or kind of encodes the relationships, what's called the similarity structure of things. So you might, for example, in medicine, I'm just off the top of my head, you might have a set of diseases that have similar symptoms. And based on those symptoms, you might try to categorize them together, right? Fever, runny nose, et cetera. Actually, what's more important is that one's a virus and one's a bacteria, you know, is the cause of this thing. And so that would be more to the meaning of the thing. And if you were to encode those in a neural network, you would want to encode them in such a way that all the viruses were near each other and all the bacteria were near each other. And so then when you do your search, you're not searching for keywords that are near each other, you're searching for things that are near each other in the similarity space. I hope that makes sense. But that's the difference between meaning-based versus kind of a keyword-based search. Anything to add, Mike?
Yeah, I mean, just to add about thinking about like molecular structure, you could have very similarly structured molecules, but the properties could be quite different depending on what property it is. And so, from a chemist perspective, maybe looking at the molecule, it could look very similar, but in property space, it could look different. And so, if you have enough examples of those things occurring, you could learn that representation using the approach Mike talked about.
Thank you so much. This audience member is asking, how do you handle messy historical experimental data? What cleaning standardization steps are essential versus nice to have?
Mike, I'm going to let you handle that one.
That's a tough question. Let me think for a second. I mean, yeah, obviously you need different kinds of data. One of the challenges is always, right, it is messy, as you mentioned. And historically, pre-LLM, we would have to try to structure that data as much as possible, and to feed that data into a machine learning model to do prediction. But now there's opportunities with LLMs and things to use unstructured text in addition to tabular data. And so this makes it much more flexible in what you can do, either to use that unstructured data directly or even extract out structured data from it much more efficiently than you could even a couple of years ago. But every problem is different, and every lab has different data in different formats. It's figuring out what matters and how you can extract that to design this kind of system. Either the specific tools within it that Mike talked about, or even then the overall system, and figuring out what tools you're going to prioritize to get started.
Yeah, so a couple additional comments. So one is you kind of need to do an assessment of whether it's worth extracting your historical data. Sometimes, for example, everything's in spreadsheets and every spreadsheet is a little bit different. You can do a lot more with that now than you used to in the past with LLMs. They can actually be very smart about it. We've built tools to handle that kind of variation to a lesser or greater degree. So that's one thing you need to think about is all of your data, your historical data versus your data going forward. You definitely should be getting your data going forward sorted so that you don't have this right? The best time to plant a tree was 20 years ago. The second best time is today. Same thing with your data, right? It would have been better to set up your data systems 20 years ago so that you have clean data that's ready for secondary analysis. The second best time is right now. So that's another guiding principle is you need to stop thinking of data as exhaust, right, from your system. It's a side effect of what we're doing, and think of it as the fuel that runs the engine, in the sense that having your data complete as an analytic data set and organized so that you can pull it in a, rapidly in a way so that it's packaged up as a product. It's packaged up not only for the project you're doing, but for secondary analysis. I would use that as a guiding principle for what needs to be prioritized and what to do. And sometimes that means organizing things that you have. Sometimes, like we had a step in a process that we observed where an expert would touch the polymer material and say it's too sticky and throw it out. That wasn't recorded anywhere. That's a piece of data, right? You have to quantify that metric and you have to quantify that step so that you actually have a complete accounting of what data are being used in your workflow if you're going to want to do other stuff with it. So like Mike said, it's the reason it's hard to answer is because every situation is a little different, but there are these kind of guiding principles or ways of thinking about it. You want complete data packaged as a product that you can use for secondary analysis is the kind of thing that you would think about. But you also want to be smart about, is it worth trying to extract all the historical data, or do we just focus on getting our new data set up for that so that it's feeding into a system that from starting with today we can start doing that kind of thing.
A great question. All right, next question from this audience member. What role does agentic AI play in materials by design?
So, all right, I'll start, Mike. So, like I said, materials by design is kind of a way of, it's kind of an endpoint in a way, like the self-driving lab is materials by design. It's the endpoint of anything that you would do with R&D with technology. And within that, there are lots of different tools and technologies that have come online over the years to make it more and more possible for more and more labs in more and more industries to kind of move further in that direction. So agentic AI is probably the biggest unlock in many ways, partly because the nature of R&D is so path dependent, right? This is part of the reason that you don't have off-the-shelf tools for a lot of R&D, is because the variability is immense, right? Project to project, scientist to scientist, lab to lab, industry to industry. There's so much variability, and software is good at rule-based kinds of algorithms. You have to be able to specify things in terms of rules, but if what I do next depends on what happened before, the rule base would explode exponentially. It's not manageable. Agentic AI has the property that matches that, which is agentic AI has a goal, and it can actually back up, it can try new things, it can pull in information, it can make decisions. And so it's got the right sort of signature to match the workflow of R&D in a way that no prior technology has. So what does that mean? We have to see how it plays out, right? There's all kinds of questions about how to make that work in practice, but that's very exciting as an affordance. So people are working on that, but there are lots of other ways that agentic AI can support. Like, as we talked about, getting your data in order is a problem, and a lot of it is because the data is unstructured, it's been collected in an ad hoc way, it's highly variable, as I described with the Excel files. That's something that agents can be very good at, and those things can be actually, we can use those today, right? So there are places along the way where we can start to deploy agentic AI to do things that would have been very expensive in the past, if not impossible, that are now, totally manageable. Mike, do you have anything to add?
Yeah, I think that's definitely a good point. I remember thinking about that a lot, like especially if you think about R&D as a spectrum, like the R side being researchy, very exploratory, by definition, uncertain. You don't know what you're going to do next, and it depends on what you find, right? Like Mike said, versus development, where you've developed a process, you've developed a reasonably well-defined target and what you're trying to make. And so you're kind of just executing. It's almost like it's not manufacturing yet completely, but you're executing a process over and over, and there's enough momentum behind that where it makes sense to like start collecting structured data and doing all the things we talked about. But yeah, agentic AI makes it really possible to do, of course, make that faster and easier if you're more of a development side of the house, but also actually make it possible, maybe for the first time in the last couple of years, to do this in a very exploratory research type of project. But yeah, there'll be options for both, and all the tools that go, all the very specific, detailed analysis tools that go into this, making that faster to create those using AI for coding assistance, and then trying to connect them all together into a larger workflow. Are all things that are moving quicker than ever. And so it'll make that accessible to more and more organizations.
This is amazing. We have about time for one last question. This audience member is asking, what have you observed in terms of the evolving role of domain expert, where your software platform and platform services are used?
Yeah, great question. I mean, there's a bit of a jump ball as far as kind of where that's going to land. But what we've seen in the past are part of the challenge we have here with using technology effectively in R&D, for some of the reasons we mentioned already, given the complexity and the variability, is you can't have off-the-shelf solutions. And so you somehow have to get the technology into the hands of experts. And so one of the things we found really powerful is to make chemists into digital chemists and make biologists into digital biologists. And they don't have to be full-blown computer science level people. You can actually do it quite efficiently, but it just unlocks a whole way of seeing the world and thinking about the world, which it kind of opens up the art of possibility to them. Like, they do things by hand and they never knew that you could automate moving files around, for example. Just that low level of thing. Or they start seeing, oh, I've got all these defects that I'm circling by hand, but if I actually collect the data, I can start to model the relationship between the nozzle and the pattern of defects. It changes the way they think about the work, and it opens up a whole new dimension. So I think that's kind of the core of how I would think about this, is that the domain expert is an enhanced domain expert, right? They're a computational scientist. They're not just a scientist. And, you know, in this, and that just gives you superpowers. And so I think that's what's happening. The other piece is kind of what I alluded to, where we have to kind of, certainly right now, domain experts are needed to figure out like how to steer the process, right? Okay, I'll give you an example. So right now, LLMs are good at playing Go. They can even be better than any human at playing Go, but they aren't good at inventing Go, right? It's that creative layer where steering the process, coming up with the goals, figuring out what are the properties of the thing that we want to make. That's still the domain of humans. And I think that's where the human expertise, and that's a much more, I don't know, it's a much higher leveraged application of that kind of expertise. So I don't know if that's a satisfying answer, but I hope it gets to your question a bit. Mike, anything to add?
Do we have time for me to add a little short bit?
Sure.
Okay. Yeah, I mean, so in my team, we work really closely with domain experts every day. And I think I've seen roughly two buckets or two categories of domain experts. One of them is kind of close to what Mike was talking about, right? Scientists who learn programming, they learn how to use computing technologies to assist them in their work. Those could be computational scientists or even experimentalists, right? Using these tools to analyze their data faster and better and automate some of their tasks. That's still a very valuable category, but I've also been seeing an emerging of another category, which is people that they don't love programming, they don't love the doing it, but they see the vision for like what it can do for their science and what they're working on. And so they unlock this idea that actually you can do almost anything, okay, in the realm of physics, but like you can do a lot of things with software. It's not just like the software you buy. Like if you can program stuff, it opens up a whole range of things you could do. And even if they're not doing it themselves, they could be really great as like a product owner or someone who has the creative idea for like, we need something that does these things. And they don't have to build it again, but they can translate those, I wish I had this, into requirements that another team can build. And they can be very effective at making sure that the right things are built with the right functions that have impact on the innovation and impact on the business. And that's been a big category that's really growing. I think people who get digital, not in details of programming, but in what can I do with this technology? And they're thinking of that and using that to transform how their teams operate and how they individually operate. And that's really powerful, I think.
Yeah, and it gets easier and easier, right? Like the technologies are now more operable by humans who are non-technical. Yeah. So, all right, back to you, Melissa.
Yeah, it's amazing and exciting at the same time. And so thank you both. That's about the time that we have right now. Thank you again, Dr. Michael Connell and Dr. Michael Heiber, for that, again, excellent and very exciting, I think, in the realm of science for the presentation. Any questions we didn't get to during the webinar will be answered by email. Thank you, participants, for being a great audience, and On24 for the technology and production services. A big thank you to Enthought for the sponsorship that made this interactive webcast possible. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. And for CNN webinars, I'm Melissa O'Mara. Goodbye.